Hey everybody, it's Mr. Canfield. I'm going to be working through the notes that we're going to be doing in class. So if you were in class this past time, we did our introduction to calculus, and we just talked about how before we knew calculus, we were able to find y values. You're able to find, average rates of change between things, but we're really limited in how we can analyze curvy things like this and groups of curves like this. We can find intersection points, but there's a lot more that we can do. And we talked about some synonyms that we have of words like positive change and negative change. You're talking about growth and decay, talking about rising and falling, static in our no change category. And we also talked about the definition of the tangent line. And so I'm not going to use a rigorous definition, super mathy, but on this page we have five different lines that we're trying to say are tangent lines, but two of them don't count as tangent lines. So this one is a tangent line, and so is this one. And this one addresses a misconception. A lot of us will say a tangent line can only touch at one point. And if we kind of ignore over here, then that's the case. So tangent lines need to touch only at one point as long as we're just looking in the neighborhood of where the point actually is. We don't really care that it hits over here. And the thing is, this one's hitting only once, but this does not count as a tangent line. So the thing that we can say is, well, it's because it's not like bouncing off of the function. And so, well, this one's bouncing off of the function. Yeah, but that's not a line. That's a ray. It's not going all the way through. And then down here, it's like, well, this one's not bouncing off of the function, and you're saying this is a tangent line. Yeah, this is a tangent line. So it's crossing it only at one point, even though it crosses over. But if we were to look really closely, we'd see on either side of it, it's not touching. So tangent lines are allowed to do this. They don't just have to bounce off, they can kind of pass through, so long as it's a glancing passing through, not a like all the way through. All right, so as long as we understand the general definition of it, we're okay. So on this page, as much as possible, I'm going to graph these by hand using what you should know from previous courses about how to graph things. And so I'm going to talk through them. I'm going to go through pretty slowly just to make sure that these 8 examples make sense. So our first one says y equals negative 2x. So the greatest power of x that I see is the power of 1, since there isn't anything written. So that tells me it's a line. And so if you remember slope-intercept form, y equals mx plus b, then, well, there's no y-intercept on the end. So I know I can start here at 0, and my slope is negative 2. Remember, since there's nothing on the bottom, it's negative 2 over 1. And literally, if you don't know any of that, you could plug in x values, get out y values, draw dots, connect the dots, win. So I'm going to go down 2 over 1 to, oh, wait. Okay. My scales on this, it's going by 2's, and sideways it's going by 1. So my y-axis is going by 2's. So I'm going to have to go down 2 over 1, down 2 over 1. I could reverse that and go up 2 and backwards 1 as well, and draw my line. So there's my line. For each equation, graph in an appropriate window and draw the tangent line at the indicated x value. All right, if I go to negative 1, all right, a tangent line is supposed to come in and bounce off. Here's the thing. This is already a line. So the tangent line, no, the tangent line is the line. So it's kind of silly. All right, now we'll get into like a real one. 1 minus x squared. So x squared is my greatest power. That means it's a parabola, and so I'll need to use what I remember about parabolas. Maybe I could rearrange this to be in a form that I'm used to with parabolas, so like negative x squared plus 1. If I rearranged it like that, oh, okay. Well, I see that it's getting moved up 1, and then it's just my parabola shape, but the a value is negative 1, which means it gets flipped upside down. So I know I've got some kind of parabola like this. Okay, And now I want the tangent line when x is equal to 0. So I'll go to x equals 0, and I want to draw a tangent line that's coming in and glancing off of it. So boom. All right, number 3. I see x cubed, so that means, oh, okay, it's going to be one of these kinds of graphs. You know, like a woo and then woo. But these terms in the middle prevent me from knowing what the heck is going on. Uno momento. Whoosh. All right, so I'm going to go in, I'm going to go y equals, I'm going to do x to the cubed, no, x to the third. It's 3x squared plus 3x minus 5. Giraffe it. All right, so we got a little in there. Oh, you know what? Since, I think, yeah, up until number 6, they're all following this kind of weird pattern. I can make my screen look just like that. So if I push the window button, I can go, and the x goes from, looks like -7, because like, well, maybe -6.5. So if I say I can say the x min is -6. No, not -60. I'll hit delete to get rid of that. The x max I'll say is 6. The x scale, that's how many units it goes before it puts another tick mark. So it's doing it every 1, so I'm going to leave it at 1. The y min looks like it's going down to -8. And we could put -9 if we wanted, and we could have put 7s there. It doesn't matter. So 8 to 8. But on the y scale, it's going every 2, it's putting a tick mark. So if I put a 2 there, then now you'll see the stuff lines up the same. And so now it's even easier. And if you had noticed, like my y-intercept for this is still -5, so that would have been simple enough to draw. And then we're like, yeah, put it in the wrong spot, Mr. Canfield. So, all right, boom. Sorry, I yell at myself when I make silly mistakes. 2, 4, 5, right? And then it looks like 1, 2.5. Between 2 and 3, it's hitting the x-axis, and I could get really accurate if I wanted to, but for the purposes of this exercise, I'm just trying to find like tangency and stuff like that. So I missed. All right, so my tangent line at 1 looks like it's gonna. Is it like gonna come in? Like that? I think it's gonna be like that. And that's more based off what I see on my calculator screen. Like it looks like it's kind of hitting there. The thing I focus on is what does it look like the steepness of my function is at that point. Whatever the steepness of my function is at that point, that's the steepness of the tangent line. That might be giving too much away right now, but it's true, so I'm going to say it. X squared minus x to the 4th. Okay, so I could find the zeros of this without my calculator, and I'm going to do that just so we can talk about it, because I know that you would have learned how to do this at least somewhat last year. So I'm going to take an x squared out of both of those and get 1 minus x squared. Right? Yeah, okay. And then I can even factor this second one as well. I can say that this is 1 plus x times 1 minus x, because it's the difference of 2 perfect squares. And so I see 4 zeros here. I see the 0 of -1. I see the 0 of 1. And so that tells me that this graph touches the x-axis at -1, and it also touches at 1. Now the 0 for this one is 0. And I didn't misspeak when I said I see the 4 zeros. X squared, that means this is x times x. Guys, that means this is a double root. That means 0 is a root twice. And if you don't remember what that means from pre-calc, it means that it actually bounces off of the x-axis. Now, I am not sure if it I'm not sure if it goes like that or if it goes like that. And there are ways to figure it out. Simple ways, like I could just plug in 1 and see that we wind up getting, oh wait, no, I couldn't plug in 1. I could plug in like a half, or plug in things in between to see what's going on. I can also just cheese my way there. And I get, he's an M. All right, so, something like that, okay. So, at x equals 1, the slope of our tangent line is going to be like, ka-chow. Yours might look a little bit different than mine, but whatevs. All right, so 3 minus x. All right, 3 minus x, that's an absolute value graph. If you don't remember, absolute value graphs are all like, I'm a V, woo! It's like a line that changes its mind halfway through. I mean, literally, that's what happens. Anyway, so the problem is it's got this 3 minus x in here, and I've thought about how to teach this one to you guys. I looked at it a couple days ago. I was like, what's going to be best for them? So I just want to remind you that this is the absolute value of negative x plus 3. And we could factor a negative out there and get negative x minus 3 on the inside. I'm doing this to show you that it's being shifted 3 to the right. And then it's negative, so it's going to turn it around this way. So it's like this, and then it's like this. But with a symmetric, I almost said symmetric, with a symmetric shape like this, it doesn't matter. You're not going to see that difference. So I'm not paying too much attention to the slope on this. What I care more about is drawing a tangent line to this one. Is that a tangent line? Sure. 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 Is that a We would actually say there's no tangent line for this one. We call this a sharp point, and because of this sharp point, I could draw an infinite number of different tangent lines that only touch right there. And that doesn't work. So we're going to get more into why this doesn't have a tangent line in the future, but right now, womp womp. All right, let's talk about e to the x. So I want to remind you, e to the x. Well, I like to start with e to the 0 because that's a nice easy one. E to the 0 is 1, so we're going to put a little bap there. Remember, e looks like schwa, right? It like gets perfectly flat off to the left, and then to the right it goes wee, and it goes up forever. So I'm going to flatten this out, get closer and closer and closer and closer and closer to 0, but never actually get there, and then over to the right, just be like, whoa, okay, so, and e to the 1. E to the 1 is about 2.7, or 2.718, blah, blah, blah. You're like, how'd you know that? Because I have a calculator, and I can go, hey, calculator, what's E? And it's like, here's that number. And I'm like, thanks. So we go, all right, so whatever. It's a swoopy thing, cool. All right, and we say, hey, what's the tangent line at x equals 0? And it's like, okay, it's right there. So it's like, bap, there's my tangent line. Wee. Okay. Now we're going to look at sinks. And it wants when x is equal to pi. Okay, this is a no-no. I'm not using this scale. So I'm going to call, let's see, I'm going to say this is pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. That's how I'm going to do this. So that means that sine of x starts at 0. At pi over 2, it's at 1. At pi, it's back down to 0. 3 pi over 2, it's down to -1. And then at 2 pi, it's at 0. And it goes swoopity swoop, swoop to swoop, Swoop to swoopity swoop. All right, and then, so it's tangent line there. Looks like it's going to be pretty negative like that. Me passing through, and that's cool. That's all right. All right, last one. Y equals square root of 4 minus x. So this one is very similar to number 5, but now it's with a shape that actually looks different, because remember that square root of x is a sideways parabola, but only half of it. And 4 minus x, well, we could pull a negative out and get x minus 4. So square root of negative x minus 4. So it's going to be the square root. It's going to move 4 to the right, and then it's going to flip around sideways. So we go 1, 2, 3, 4, but instead of going swoop like that, I'm going to go swoop that way. And just to help yourself out, plug in 0, or plug in a couple easy numbers. Plug in 0 there, we get square root of 4, which is 2. So we'll go swoop. And we want the tangent line when x equals 4. And here's a problem. It stops here. Drawing this tangent line, again, we've got a similar situation where it's like, oh, I could draw all sorts of tangent lines, and none of those really make sense in this problem. And you might see, like, well, wouldn't it, like, if we were to kind of continue this and get this, like, sideways parabola for what it really is, the tangent line should be straight up and down. And I think you make a really good argument saying that, if you're kind of thinking like that. But this is just the positive square root. So if none of that made sense, don't sweat it. Since it's a point like this, we can't find the square root again. I mean, the tangent line again. So hopefully that is helpful for you to go through and do some pre-ectus. So I learned a lesson just now. Here's the lesson that I learned. I don't know if you can see it, but it like is bleeding through my paper. So I might start working in pencil in this book, which makes me sad. I love writing in pen. Pen's my favorite. So, all right. So anyway, I hope that's enough for you to attempt the homework assignment. And yeah, have a good one.